Hello and welcome to another LeetCode video. Today we're going to be working on sliding window maximum. So in this problem, you're given an array of integers and there's a sliding window of size k, which is moving from the left to the very right. You can only see k numbers in the window each time the sliding window moves right by one position. Return the maximum sliding window. And so at first, when I read this problem, I just thought like, hey, this is a really easy problem. I thought they just meant like the maximum sum or something, so you would just have a basic sliding window, pretty straightforward. Like you just have a sliding window, you'd move it, you would get the sum. Doesn't seem hard. But actually what they mean is they want the maximum number in the sliding window at every point. So here it would be a 3, here it would be a 3, here it would be a 5. Here it would be 5, 6, and 7. And you want to return the array of maximum numbers at each position. So I know it's not like the best explanation, but that's what it is. So the problem with this, let's actually write it out here. So if we have numbers 1, 3, -1, -3. Might run out of space here, but it's okay. 3, 6, 7. Okay. So the problem is if you have some sliding window and you move it, you didn't know if you lost your maximum or not, all right? Like let's say your sliding window is here, and maybe this is like a 0. Well, you don't know that when you moved your sliding window, you lost your maximum, because how do you keep track of what number is your maximum in constant time, right? You wanted to try to do this in constant time. I mean, you could like say it's your current maximum or something, but then how would you know it is later on? Like there's just all kinds of like errors you can have by trying to keep track of the maximum, essentially. And so we need to find a better way to do that. We need to figure out like how do we keep track of a maximum? And let's just think of a few cases. So first of all, notice how as you go through your sliding window, like let's say you go from this state to this state, right? The number on the left gets removed before the number on the right, right? So if we have a sliding window with a bunch of numbers, this number is going to last the longest. Okay, well, what if that number also happens to be the biggest number, right? Like let's say this is our biggest number and all of these numbers are smaller and we know these are all getting removed first. Is there something we can do to help us solve that kind of problem? And actually it turns out there is. So what we can do is we can make sure that the numbers we're saving are monotonically decreasing. And so what I mean is, let's say we have, so let's say this is, let's say it's actually like this. So we have 3, 1, -1, -3. So this is actually monotonically decreasing, right? It's decreasing. Then we have a 5. And we know that for this sliding window, this 5 is going to persist the longest, right? It's going to move over here, and then it's going to move over here, and then it's going to move over here. So we don't need any of these numbers. Like as long as we have the 5, like these numbers will be irrelevant. Unless there's something bigger later on, but we'll take care of that. But like this will never be, none of these will ever be our maximum, so we don't care. So what we can do is we can say, okay, let's say we have some kind of data structure that holds these numbers. Well, if we put in a 5, we can just say, okay, is 5 greater than this? And remember, 5 is going to last the longest because it's on the right. Is it greater? Okay, let's get rid of that. Is it greater than this? Yes, it is. It's greater than this. Let's get rid of this. And now we just store the 5. Obviously, we need to also store some kind of like an index because we need to know when to get rid of it. But essentially, once you can recognize that if you have a bunch of numbers and you have the 5 is the only one that matters. Like if a number on the right is bigger than a number on the left, the number on the left, we can get rid of it. So essentially, our stack is always going to be decreasing, and then we can easily get the biggest number because if our stack is always decreasing, our biggest number is always going to be the number on the left, right? And then we're also going to store the index of that number. So you can use a couple ways. You can either just store the index of that number on the left, and then you can get it. But we're actually going to just store an array of the number and the index of that number. And then we can just check, like for every single index, like as our left and right moves, we can just check, like, okay, is our index still in our sliding window? Because we can easily maintain this. And if it's not, we can get rid of it. And what we're going to actually do is we are going to use a Deque. And a Deque is going to allow us to pop from the left and the right, and that's going to be very useful. So let's go through this. So essentially what's going to happen is, let's just go through this example. So first we need 3 numbers. So let's have a results array. First we need 3 numbers to even be doing anything. So our Deque is going to take in the 1. Then it's going to go to the 3, and it's going to say, okay, is 3 greater than the 1? If it is, we don't care about the 1. And remember, we're going to take in a 1 and the index of the 1, so it's going to be like 1, 0. But yeah, 3 is greater than the 1, so we don't actually care about this 1. So we're going to get rid of that. And we are going to put in the 3 and its index. So 3 and index 1. And we're not writing to the result because we need to actually be over here to write to the result, right? We need to be on the kth number to write to the result. Like if we have our sliding window like this, that's not big enough. Okay, now for the -1, is -1 bigger than 3? No, it's not. So we're going to add it to our stack, or deck. So we're going to have -1 with index 2. And now our right is over here, right? So now our sliding window is big enough to get a maximum. And remember, since we are storing a decreasing maximum, the maximum is always going to be the number on the left. So we're going to put this right, we're going to put this value on the left in here. Now we will update our stuff over here, and we're going to say, okay, is -3 bigger than -1? No, it's not. Okay, perfect. So let's write -3, and its index is 3. Okay, and let's get its maximum. Let's get the maximum again. So, oh, and by the way, we have to do a couple more things. So we have to see like where our left and our right is. So our right is over here. Our left. So when we moved our right, our left actually moved from this number to over here. So if there was a left here, it would be deleted. So now let's just have a left, and we'll have a right there. Okay. And so we need to check, like, is our left, is this index the same index as here? It is for now, and for now, as you can see, like, it is in our valid sliding window, but we're gonna have to check for that later. Okay, so we stored our 3 again, right? Because 3 is gonna be our biggest number. Okay, now let's move our right. And before we move the right, we also need to move the left over here, right? Because the sliding window needs to be length 3. So we're going to check, is this left value in our stack? It's going to be pretty easy to do. It's going to be the leftmost value always. So yes, it is. We can check by the index. So this is index 1. So yes, it is. So then we need to delete this element because now it is no longer in our queue. And we're going to use a queue because we're going to want to push to the back and pop from the back and also pop from the front. Okay, so now our left is going to move over here. So let's get rid of some of this. Okay, now our left is over here. And for our right, we're going to check, okay, is 5 greater than this -3? Yes, it is. So we don't need the -3. Is 5 greater than this -1? Yes, it is. So we can actually delete the entire stack now. And we can put in the 5 because we need a decreasing stack and we had -1 and -3. So now our stack will be 5 and the index of the 5, and that is 1, 2, 3, 4. Okay. Then we will take our maximum. So our maximum here will be 5. It's always the leftmost thing in the queue, I guess, or deck. Okay. Now we need to update our left because our left will be out of bounds in the next iteration. So we're going to update that left, and we are going to move it over here. But before we move it, we're going to check, is this -1 in our queue? It wasn't. We deleted it earlier, so we're good there. Let's get rid of this. Let's get rid of this. Okay. And so now we need to move our right. So let's do that as well. So let's, yeah. We are going to move our right over here to the 3. And then we're going to say, okay, is the 3 greater than the 5, right? Is this 3 greater than the 5? Because our stack needs to be decreasing. No, it's not. So we can add it into our stack or queue. And the index here is 5. Okay, now we're going to take our maximum. Our maximum is always the leftmost value, so it's still 5. Okay, now we are going to, so this should be right. So now remember, we're going to move our left once again. So we're going to move our, and you can move your right first. You can move your left. Either one works. So we're going to move our left. We're going to check for this -3. This -3 is not in there, but we have to move our left. So let's do that. Let's move our left over here. Now let's move our right as well. One more. Okay. And now we are going to, oh, this is right. And now we are going to check, is the 6 greater than the 3? Yes, it is, so we don't need the 3. Is the 6 greater than the 5? Yes, it is, so we don't need the 5. Remember, seconds to be decreasing. So now we can get rid of all these numbers once again. And we can put in the 6 along with its index. So we can say 6, and its index is 1, 2, 3, 4, 5, 6. Okay, now we're going to get the max, which is 6. Remember, max is always the leftmost number. Now we are moving our left and we're moving our right. So in this case, our left is not in our array because we just deleted it. So our left is going to move and our right is going to move. So let's do that. So our right is going to be over here. Our left is going to be over here. And then we are going to put in the 7, but before we do have to check, is 7 greater than 6? Yes, it is, so we're going to delete the 6. So we're going to delete this whole stack again, and we're going to put in 7 with index 7, like this. We are going to get a maximum, which is the leftmost value, which is 7, and then finally we are out of bounds. And so that's how you do it. You have a left and a right, and you make sure your stack is always strictly decreasing. That way your leftmost value, your biggest value is always on the left side of the stack. And then you just check every time you update your left, like, hey, is my leftmost value still in the stack? If it is, or Q, if it is, I need to pop it. That's why you need a Deque, because you need to pop from the left when your left moves, and you need to pop from the right when you insert elements. So you need both of those. Okay, so now we have enough to be coding, so let's do that. So we are going to make a left, and we'll just make that equal to 0. We are going to make a result, and we are going to make a Deque. So we'll just call that like window Deque. And then we can use the right in place, so we can just say for r in range length of nums. You can also do an enumerate, either one works. And you can also, like I said, you can store the index instead of the number. Technically, if you had the index, it would also work. So, but I'm just going to store an array of index number because it's the same space complexity. It might give you like a little bit worse on LeetCode because it should be O of 1, but that's okay. Okay, it just looks a little bit cleaner that way. So now what we have to do, remember, we are going to be checking as long as there is a stack and the number we're currently on is greater than the last one, we're going to have to pop from there. So we could say like while, or I guess like Deque. So we could say while window and nums r is greater than or equal to, we want strictly decreasing. So nums r is greater than or equal to window -1. So it's going to be the last value at index 0 is going to be the value, and then at index 1 will be the index. We can just do a pop here. Then we want to insert our element, so we can say window dot push. Or sorry, dot append, too much JavaScript. Then we're going to insert an array here, so it's going to be nums r and r. Now we also need to check, is our left. So I think the order I did this in is a little bit different. I guess I can, it doesn't really matter which way you do it. I guess I'll leave that for now. So now that we appended our number, what we have to do is we have to check, is our sliding window actually long enough, right? Because like right now our sliding window is 1 number, when we need our sliding window to actually be k numbers. So we can say if r is greater than or equal to k minus 1, right? So if r is 2, that means we would have a sliding window here, which is long enough. Then we would do the result. So we're going to say result dot append. And then we should always have a stack here, so we don't have to check for that. So we could say window 0, 0, right? The first element, and the 0 is going to be the number. Okay, now we do that. Now also, if this is the case, we need to update our left. But before we do that, we need to check, is our left in the stack? So if window 0, 1 equals the left, then we need to get rid of it. So we can just say window dot pop left, and we are going to increase the left regardless. Okay. Yeah, I think that's all we need here. And now I think simply we just need to return a result and hope we don't have an error. See what happens. And we do. Okay, so yeah, you can see it's pretty efficient, and yeah, if you want this to be a little bit higher, instead of appending like this, you can append one number and you can use a little bit less variables. But because it's O of 1, it's going to be really like a small difference in memory is going to make a big difference in percentage here. Like if you get rid of the left variable, which you don't really need, you can calculate it in place and so on, but then your code's going to be less readable, so it's not super important. It's still going to be O of 1. Okay, so let's go over the time and space really quick. And so for the time, so I guess it's actually, sorry, it's not going to be O of 1, it's going to be O of n, but either way it's going to be O of n because you have this Deque, right? It just might be like O of 2n when you save 2 numbers as opposed to 1, which would give you a worse number on LeetCode, but in a real setting, it's the same thing. But that's an optimization you can make. Instead of appending the nums and the right, you can just get the value from the index itself, right? So I guess we could do that really quick just to show you. So and we could calculate this left in place as well, actually. So let's try to do both of those. So instead of appending the right and the number, let's just append the number. So we can just append the index. And now this is the same. Now res append window 0, 0. So this should just be nums window 0 now, because this is just an index. And so if windows, so this should be nums. And let's try to calculate L in place. So we can do that as well. So we can just say if nums, so L is going to be right minus k plus 1, I believe. Let's just double check that. So if right is 2, then 2 minus 3 is going to be -1, and then, yeah, that's going to be correct. Okay, so I think it's like this. We don't need this now. We can just do that in place, get rid of this left, and see if we have a little bit more efficiency. I mean, yeah, it doesn't really matter, but for the, you know. Okay, let's see. So this should be nums window like this. And there we go. K equals 1. See output 1, 1. Okay, so we did get something wrong here, which is interesting. Okay, so if nums window 0, oh, right. So this needs to be the index, not the num. So this needs to be window 0. Hopefully we got it now. Okay, so yeah, you can see it's a lot more efficient if you just get rid of a few variables, but realistically it doesn't really matter. And it's a little bit harder to read this way. Okay, so for the time, it's going to be O of n because we're essentially iterating through our numbers. Yeah, so the time is going to be O of n because we're just iterating through our numbers in constant time. In worst case scenario, we would add every number to the queue and we would delete every number from the queue, so that would be O of n. Now for the space, it's going to be O of n as well because we are using this Deque. So let's say our k is like length n. So that would be really bad, right? Like if our k is length n and our numbers are decreasing to begin with. So let's say k is like 5 here and our number's like this. Then we would store the entire... So I guess space wouldn't... You'd still want to not use O of n. I think you would want to use O of k to be more accurate for the space. Because the Deque can only be as big as k because k is a sliding window. So worst case scenario, you're storing the entire sliding window. But yeah, that's going to be all for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.